Okay, picture this for a second. We're standing on the edge of a map,
Right.
but it's not a map of, roads or rivers or buildings.
Yep.
We're looking at a map of API City.
It is a striking visual to start with,
Yeah.
and it sets the stage perfectly for what we're tackling today.
It really does, because on one side of this river, you've got this chaotic, almost dystopian landscape. It's smoky, messy, wires everywhere.
That's the spaghetti code.
Exactly, that most of us have dealt with. And on the other side, a gleaming, structured metropolis. Chrome, glass, perfect grid lines.
And connecting them is a massive bridge.
Right. And that bridge is the topic of today's deep dive. We are looking at API design patterns, the architect's blueprint. We've got a whole stack of research and diagrams here that treat API design not just as code, but as civil engineering.
It's about building infrastructure that connects that chaos to order.
And honestly, treating it like civil engineering seems like the only way to survive in modern software. Usually when people think of APIs, they think of JSON brackets or endpoints.
Sure, but the research we're looking at today argues that an API is a promise. It's a contract.
And a high-stakes one at that. There's a quote right at the top of the stack from Joshua Block that, frankly, gave me a bit of anxiety.
Oh, I know the one.
He says, public APIs, like diamonds, are forever. You have one chance to get it right, so give it your best.
It sounds dramatic, doesn't it? Forever. But he's absolutely right. Think about it. If you change a website's interface, users might grumble. They might have to relearn where a button is, but they figure it out.
Right.
If you change a public API, you break the code of every company building on top of you. You break their business.
That is a terrifying thought. And that's the cost of chaos mentioned in the philosophy section here. The notes highlight that bad design leads to breaking changes, support nightmares.
And massive technical debt versus the value of order reusable modules, happy developers, stable evolution. It creates trust.
So how do we design for that trust? The guide suggests we start with the most fundamental choice, the language of interaction.
This is what they call the Great Divide. It really comes down to a choice between nouns and verbs.
Or, to get a bit more technical, resources versus intent.
Exactly. This is the first fork in the road for an architect. Are you building a system based on things or actions?
Let's break that down, because I feel like everyone just defaults to one answer. The noun approach, that's REST, correct?
Right. REST, or resource-oriented architecture. It's the standard for a reason. It's declarative. You aren't telling the server how to do its job. You're just handing it a resource, a noun, and saying, here is the new state of this thing.
The example in the notes is post-AP orders. You're focusing on the order as the entity.
Precisely. You don't say process payment and ship box. You just say, here is a new order. The server figures out the rest. And the beauty of this is predictability. It leverages web standards we already have, caching, for instance.
And caching works beautifully with REST.
It does, because the internet just knows how to cache a resource.
But you have the verb approach, the intent-oriented style. This is RPC or gRPC.
This is imperative. It's much closer to actual programming.
Yeah.
You are issuing a command. The example here is create order. It looks like a function call because that's essentially what it is.
So why would I choose that over REST? REST seems so universal. If I'm building a modern system, why go back to what feels like remote function calls?
Performance and specificity.
Yeah.
If you're doing something complex that doesn't fit neatly into create, read, update, delete, say, triggering a complex calculation, or a very specific server-side action like restart server, RPC is often just cleaner.
Okay.
And it's usually lighter on the wire, which matters a lot for internal microservices where every millisecond counts.
Then there's the third player, which feels like the popular kid in class right now, GraphQL.
I see this everywhere.
The notes describe this as a hybrid, but also as a shift in power.
That's the best way to describe it. In REST and RPC, the server decides what data you get. In GraphQL, the client decides.
It's query-based.
Exactly. The client says, I want the user's name, their last 3 orders, and the shipping status of the first order. And the server sends back exactly that. Nothing more, nothing less.
Which sounds amazing for a front-end developer. No more overfetching data. So why don't we just use GraphQL for everything? Why mess with REST at all?
It is amazing for the front end, but, and there's always a but, in engineering, it pushes immense complexity to the back end. The source material has a specific tip here. Best for graph traversal and custom views. but it warns against using it for everything.
Because it's harder to optimize.
That's a big part of it. And notice the visual representation in the diagram. GraphQL sits right between the rigidity of REST and the specific actions of RPC. It's a powerful tool, but you lose some things, like simple HTTP caching, because every single request can be unique.
Right, you can't just cache the user page because every client might ask for different fields on that page. That makes sense. So, okay, we choose our language. Let's say we go with REST because we want that cacheability. We build our shiny V1 API. We release it. But as we established, APIs are forever. But business requirements aren't.
They change next week.
So how do we handle that without breaking that forever promise?
This brings us to probably the most contentious topic in API design: versioning, or as the blueprint calls it, future-proofing.
The contract.
The contract. The guide presents three main strategies for signaling that the contract has changed. The first is path-based.
That's the classic api.example.com/v1 orders. It's right there in the URL.
It's the most common for a reason. It's explicit. You can look at the URL to know exactly what you're dealing with. And importantly, it's very cache-friendly. V1 orders is a different place than V2 orders.
But the critique here says it's coarse-grained. What does that mean?
It means that usually when you bump the version in the URL, you're versioning the entire API. You're telling developers everything here might be different now. It's a big psychological shift.
Okay, so compare that to header-based versioning, except version.v1.
The purists love this one. The source calls it the cleanest approach. Your URL stays beautiful. Just api.example.com orders. The version is hidden away in the metadata.
But I'm looking at the downside here. Harder to test. I'm trying to picture this. If I'm a developer and I just want to see what the API returns.
It's a pain. Think about it. With a URL version, you can paste it right into your browser address bar and see the JSON.
Yeah.
With header versioning, you can't just use a browser. You need a tool like Postman or a terminal to explicitly set that header. It raises the barrier to entry for someone just exploring your API.
That's a really practical point. It's about empathy for the developer, right? If I can't just click the link, I might give up.
Ease of use matters. A lot.
Then there's the middle ground. Query parameters.
Yeah.
AP version V1.
High visibility, easy to paste in a browser. But some caching systems ignore query parameters by default. So you might accidentally serve V1 data to a V2 request if you aren't really careful with your infrastructure configuration.
It seems like there's no silver bullet here. But here's something that caught my eye. There's a flowchart called the anatomy of change. It essentially asks, do you really need a new version number?
This is crucial because not every change is a breaking change. We distinguish between non-breaking, which is additive, and breaking, which is subtractive.
So additive is what? I add a new field to the user profile.
Exactly. Say you add Twitter handle to the user response. Old apps that were built before that field existed, they just ignore it. They don't know to look for it, so it doesn't hurt them.
That's backward compatible.
Right. You don't need a V2 for that.
But the red zone is breaking changes.
Renaming a field. Deleting a field. Changing a generic name field into separate first and last fields. If an app expects a string and gets an object, or expects a field that just isn't there anymore, it crashes.
And that demands a new version.
It demands a new version.
There's a concept at the bottom of this chart that I don't hear discussed enough. Forward compatibility. It mentions messaging and queues.
That's a deep cut, it asks. Can your old code handle new messages? Let's say you have a fleet of servers. You deploy a new version to half of them. A new server sends a message with a new field to an old server. Does the old server crash?
Or does it gracefully ignore what it doesn't understand?
Precisely. Designing for that resilience, making your system tolerant, is a hallmark of a senior architect.
Let's shift gears to the mechanics of running this city. We have to manage traffic, specifically mechanics of scale and control. The first big challenge is something every app has: lists.
1 million users in a database. You can't send them all at once.
Pagination. It sounds boring, but getting it wrong kills performance. The traditional way is offset-based, page 1, page 2, page 3. The request is limit 100, offset 500.
Simple to understand, easy to code. But it has two fatal flaws mentioned here. First, performance.
Why is it slow? If I ask for page 100, isn't it just grabbing those rows?
Not exactly. That's the trap. In most SQL databases, if you say, give me rows 1 billion to 1010, the database has to count through the first million rows to find the starting point.
It actually scans them.
It scans them, counts them, and then throws them away. As your data grows, your later pages get slower and slower.
That's painful. I never realized it did that. And the second flaw.
Stability. Imagine you are looking at page 1 of a list of tweets. While you're reading, 5 new tweets are added to the top. Everything shifts down by 5.
Right.
When you click next page, the database just grabs the next 10 items, which includes the 5 items that were pushed down from page 1. You see duplicates.
I've seen that. I scroll down a feed and see the same post twice. That's offset drift.
That's at the drift.
So the alternative is cursor-based. The diagram calls this robust.
Yes. Instead of saying page 5, you say, give me 10 items after this specific ID. You use a cursor, a pointer to the last item you saw.
So even if new stuff comes in at the top, my pointer to the last item hasn't moved.
Exactly. It's rock solid stable for real-time feeds, and it's lightning fast because the database can jump directly to that ID using an index. No counting required. You lose the ability to jump to page 50. You can only go next, next, next. It's great for infinite scrolling, terrible for a directory where you want to skip ahead.
Now, controlling the view brings us to filtering. We have 2 visuals, a filter pipeline and a controlled valve.
This is the classic balance between flexibility and security. Approach A, the pipeline, lets the user send almost raw logic. Snowfall, 0.5 AND, country Denmark.
It looks like SQL.
It basically is SQL, and that's the danger. The risk analysis here screams about SQL injection. If you let users pass raw logic, you have to be incredibly careful they don't trick your database into revealing things it shouldn't.
So the controlled valve, approach B country Denmark, is safer.
Much safer. It's explicit. You, the developer, have to write specific code to handle the country parameter. It's more tedious, sure, because every new filter requires new code, but you know exactly what's going into your query.
Let's move on to when things go wrong, because networks are flaky, the Wi-Fi drops, the server hiccups. We have a section on reliability and respecting time, and the first concept is idempotency.
Idempotence.
I always trip over that word. Help me out here.
It's a mouthful, but it's a lifesaver. It basically means making the same request multiple times should have the same effect as making it just once.
Okay, the scenario in the diagram is a classic. I'm trying to pay you $10. I click pay. The little spinner spins, my Wi-Fi blips. I don't know if it went through. So I click pay again.
And without idempotency, you just charged me $20, and I am not a happy customer.
So how do we fix it? What's the pattern?
The idempotency key. Think of it like a unique receipt number generated before you pay. You send the payment with key ABC. If the network fails and you retry, you send key ABC again.
And the server sees that.
The server looks at it and says, wait, I've already processed a payment for key ABC. I won't charge the card again, but I'll show you the success message.
It's like a safety latch? That's brilliant.
It's essential for any financial API.
Now, what about when the client is the problem? They're hammering the server. Maybe a bug in their code is making them retry 1,000 times a second.
Exponential back off.
This is about teaching the client manners.
It is. If a request fails, don't retry instantly. Wait 1 second, fail again, wait 2 seconds, then 4, then 8.
Give the server breathing room.
Exactly. If the server is struggling, hitting it harder won't help.
And if they don't take the hint, we have the rate limit gate.
This is the server protecting itself. You get 600 requests per minute. That's it. If you go over, the gate slams shut. HTTP 429. Too many requests.
But there's a polite way to do this, right? The header retry after?
Yes. Don't just say no. Say no and come back in 30 seconds. It saves the client from just guessing and hammering you again.
One more reliability pattern here that I think is underused. Long-running tasks. The 202 accepted pattern.
Oh, this is vital for user experience.
Yeah.
Let's say you ask the API to generate a massive PDF report or process a video. That might take 30 seconds. You cannot have the user's browser just hanging there loading for 30 seconds.
Build timeout.
It'll time out. So the pattern is you acknowledge the request immediately. You return a 202 code, which means I heard you and I'm working on it, and you give them a tracking link. Go check this URL for updates.
So the client can just pull that link, are you done yet, are you done yet, until it says complete.
Exactly. It frees up the connection. It's the difference between waiting in line at a coffee shop versus
taking a buzzer and sitting down.
Exactly. You can go do other things while the work happens.
I love that analogy. Moving deeper into the infrastructure, let's talk about the data itself. The life cycle of data, specifically deletion. I see a toggle switch here versus a trash can.
Soft delete versus hard delete.
Soft delete is just hiding the data, right?
Yeah.
Is deleted true?
Right. The data is still there. The pro is obvious. If a user deletes something by mistake, you can restore it instantly. It preserves history.
But the con listed here is GDPR risk.
That is a huge one.
Yeah.
If a user exercises their right to be forgotten under GDPR and you just flag their data as hidden, you haven't really forgotten them. You're non-compliant.
Plus, from an engineering side, now every single query in your entire application needs to include where is deleted false.
And if you forget that clause just once, you leak deleted data.
Contrast that with hard delete.
Scorched earth, it's gone. It's cleaner, it's compliant, but it's irreversible. Usually sophisticated systems use a hybrid soft delete for 30 days, then a background job hard deletes it.
Protecting that data brings us to the fortress, core security patterns. We have a diagram of a bank vault.
3 layers. Can't skip these. First, encryption TLS. If you are not using HTTPS, you are not building an API, you are broadcasting secrets.
Plain and simple. Then authentication versus authorization. I feel like these get confused constantly. Auth-in versus auth-c.
Think of it like a building. Authentication, auth-in, is the security guard in the lobby checking your ID badge. Who are you? Okay, you are Dave.
And authorization.
Authorization, auth-c, is which rooms your keycard opens. Just because I know you're Dave doesn't mean you get to walk into the server room or the CEO's office.
And that's where the principle of least privilege comes in.
Exactly. Give users the absolute minimum access they need to do their job, nothing more.
The mitigation section here shows a robotic spider, a scraper bot being blocked by lasers. We talked about rate limiting, but what is this dry run concept validatingly true?
I love this pattern. It allows a client to say, hey, I want to submit this huge order. If I did, would it work?
It's a rehearsal.
It is. The server checks the validation, checks the inventory, but doesn't actually charge the card or ship the box. It's fantastic for complex forms. It lets the client debug their data without clogging up your database with failed attempts.
And finally, human hacking. A reminder that social engineering exploits the user, not the code.
You can have the best encryption in the world, but if your admin gives their API key to a support agent in a phishing email, it's game over.
Security is a people problem as much as a code problem.
Absolutely.
We're nearing the end of our blueprint. The source material wraps up with the golden rules of API design. It's a checklist. Let's run through these quickly.
First, tailored. Don't build a generic API if you don't have to. Build for your specific use case, mobile, IoT, AI.
Second, and this is my favorite, hard to misuse.
Simple tasks should be easy. Errors should be difficult. If a developer has to read 50 pages of documentation just to make a generic request, you failed.
Maintainable, evolve without breaking, respect the versioning strategies we discussed.
Secure. Validate everything. Never, ever trust the client.
Efficient, use compression like gzip. Don't send 5 megabytes of JSON if you can send 50 kilobytes. And finally, communicative. Use standard HTTP codes.
Oh, this one is so important. If I ask for a resource and it's not there, send a 404. Do not send a 200 OK with a JSON body that says error, not found.
Because it breaks all the automated tooling.
It does. Speak the language of the web.
We end with the final blueprint. We're back to our bridge metaphor. But now it's not just a sketch.
It's detailed. We see the TLS encryption shields protecting the cars. We see rate limit gates at the on-ramps. We see dedicated lanes for V1 and V2 traffic so they don't crash into each other.
And we see the cursor streetlights keeping the traffic flowing smoothly. And the quote returns, "Strive for beauty and trust your gut."
It really is about craftsmanship. When you build an API, you are building a tool for another human being to use.
That connects perfectly to that hard to misuse rule. It makes me think about design as empathy.
That's the takeaway. Are you designing a system that makes the user feel smart? Or are you designing a system that punishes them for not knowing the secret handshake?
Great design is about empathy for the developer, who has to use your tool at 3 in the morning when their production server's down.
That is a powerful thought.
Next time you're frustrated with a piece of software, ask yourself, was this designed with empathy? And if you're the one building it, well, now you have the blueprint.
Build bridges that last.
Thanks for diving in with us. We'll catch you on the next one.